Hi there everybody, welcome to the next lecture in the electrochemistry series, which is going to be dealing with galvanic cells, which are sometimes also referred to as voltaic cells. So we're getting ready to set up how we could actually develop a crude battery given redox reactions and their potential to generate electric current through electron transfer. So we're going to start with a bit of a attempt to make a crude battery through drawing. You'll have to forgive my drawing skills. I am certainly not an artist. All right, but what we're going to start with is two beakers. And these beakers have some solution in them, which we'll represent here. And dipped into the solution are two metal plates, or rods, however you want to view them. Okay, and the two metals that we're going to work with here, the first one will be zinc, so we'll just label this as Zn, and the second one will be copper, so we'll put Cu here. Now, when we do this, we are going to have a solution of similar based metal, but in its aqueous form. So here, we're going to generate zinc 2+ in its aqueous form, and here we're going to generate copper 2+ in its aqueous form. All right, now the solutions themselves are going to be zinc sulfate, so that will be what's responsible for generating the zinc 2+, and the copper sulfate will be responsible for the copper 2+ ions in solution. All right, now we're going to have a wire that connects these two electrodes, which is what we refer to the metal plates as. And up here in the middle, we're going to have some sort of a device. So if you've seen a crude battery set up before, a lot of times it'll either be a voltage meter or a light bulb or something of that nature. But we're going to run some wire between the two electrodes, and the electrons are going to flow in this direction. So it goes from the anode to the cathode, and we're going to come back to that term in a couple of minutes. Okay. And typically when we utilize these devices, the electron flow is going in one direction, right? So in a redox, the electrons are transferred from one metal to another. They're not really batted back and forth. Now you can reverse this process by putting some energy in and making it a non-spontaneous process that is driven forward. But that requires something called an electrolytic cell, and we will take a look at that down the road. All right, now there's something missing here that's very important, which is that we're going to need what's called a salt bridge. So because we're dealing with electrolytes in solution and we're transferring electrons back and forth, we're going to have the potential to build up a lot of positive and negative charge. And the way that we help with that buildup is by utilizing a salt bridge. So a lot of times you're going to see this as maybe a glass tube or pipe that is inverted in between the two beakers, and there's some cotton plugged on each end. All right, the salts we're going to use in this example will be potassium and chloride. So potassium chloride can be used as the intermediate salt in the salt bridge. And you have to have a salt bridge here because as you start piling up charge, whether it be positive or negative, you have to have the corresponding ion that can help balance that out. So if there's a lot of positive charge buildup, then you need to send the anions there. If there's a lot of negative charge buildup, you have to send the cations there. Okay, so we have to take a look here. What is going to be oxidized in this case is that zinc is going to end up going from zinc metal to zinc 2+, so it will be oxidized. We have zinc solid from the electrode that is going to go to zinc 2+. All right, now this is an oxidation because it's a loss of electrons, and the oxidation is going to occur at the anode of the battery cell. Okay, now we also have the cathode. That's where the reduction will occur. So copper is going to receive the electrons to become solid copper. Okay, and then this is the reduction portion. This is the cathode. So one of the ways that I remember this is that A comes before C in the alphabet and O comes before R in the alphabet. So A and O go together and C and R go together. Okay, the anode is where oxidation occurs. The cathode is where the reduction occurs. And it is going to be important that you can differentiate between the two when we start calculating the overall voltage that is produced by a galvanic cell. All right, so when we take a look at this, there's a total of 2 electrons being passed back and forth. So zinc loses the 2 electrons, copper gains the 2 electrons. And these electrons are going to be passed back and forth through the device, and that's what essentially is going to power the device. And sometimes we talk about that as E cell or electromotive force, but we'll get to that in a second. Okay, so these 2 electrons are going to be passed, and that's what will power the device. It is important, again, that your salt bridge contains these ions because you're going to have too much buildup at different parts. So the cathode is going to have the cations because there's too much negative charge that can build up in the cathode. And because of that, you're going to have your cations headed towards the cathode. So that would be anything that is a positive charge is going to move towards there. And then you can have a buildup of positive charge at the anode. And so this is where you're going to want to send all of your anions. Okay, and they will work their way through the salt bridge in solution. And the salt bridge prevents the excess charge buildup when we're working with these types of things. So the voltage is produced, and we can talk about this in a lot of different ways. The most common way to talk about it is cell potential. Okay, but there's a bunch of different words that are thrown around when we're talking about this. So a lot of times you may see this referred to as EMF, which is electromotive force. Okay, and then sometimes it's also just referred to as E cell, like this. And you can have E naught cell, and the naught stands for standard conditions. So similar to when we did thermodynamics and we talk about delta G or delta S or anything of that nature, we would sometimes go to a chart and we could find the standard values on a chart. And that was under certain conditions. So here we're also going to have certain conditions for a cell battery if it's going to be standardized, and the standard conditions for the cell is that we should be operating at 1 atm, we should be operating at 25 degrees Celsius, and the solutions should be at 1 molarity. So when we're talking about the zinc and the copper solutions, if we're going to use standard values off a table, those need to be at 1 molarity. Now there are ways around that, and in the future we will do a lecture on what's known as the Nernst equation. And the Nernst equation allows you to get around standard conditions when you have molarities that might vary away from 1 molarity, because that's a common occurrence. So there's an easier way to write out a galvanic cell. It would be a pain if every time you wanted to represent one, you had to draw this entire diagram out. So the way that we represent it when it's written is the notation as follows. You're going to take the anode first, so it is zinc solid. And then we put a single line to represent what's known as a phase boundary. A phase boundary means I'm no longer solid, I'm going into a different phase. Because zinc solid is going to go to zinc aqueous 2+. Okay, and we can note to ourselves, a lot of times you're going to see a concentration here. It's 1 molarity, because we're talking about standardized. Okay, then there's a double line. The double line stands for the salt bridge. This is the physical barrier or separation between the two solutions. Right? And then we're going to end up with the copper 2+, which is aqueous 1 molar. Phase boundary, and then that would plate onto the copper solid as the battery is running. Right? So here we have the anode, and here we have the cathode. So this is a much cleaner and certainly less time-consuming way to refer to a galvanic cell without having to draw all of that out. But it's important that you understand the concept of what's going on here. And I also want to mention, when you work with galvanic cells, you have to make sure that these two solutions are separate from one another, connected with the salt bridge. So I cannot just take the zinc sulfate and the copper sulfate, mix them together and put the two electrodes in the same solution. So there will be redox chemistry occurring there, but the electron transfer is going to go directly between the metals in that case, and it's not going to be powered to an external device, which is really what we're trying to harness or take advantage of here. So keep in mind that the setup, you do have to have two separate half cells, as we would call them, in order to make this work. If you put it all into a single cell and you're not keeping these two separate, then you're not going to have the same ability to generate electric current. Same thing with a salt bridge. If the salt bridge is missing, the charge piles up too quickly, you're going to have an ineffective battery that will not be able to hold or provide charge for very long due to that electronic buildup. All right. So if we take a look at how much power can I actually produce here, or how much electrical work can I produce, it turns out that what we need to look at is the zinc copper E cell, right? So the zinc copper E cell is going to be equal to 1.10 volts at 25 degrees Celsius. Now, when we talk about this, this is the voltage for the entire cell, the whole entire setup. So if I were to come up here and place a voltage meter that could take readings here, I'm going to get 1.10 as my reading as the electrons are being passed through. Now, you can do this for an overall cell, but the question is, how can we deal with half cells? So if I want to find out just the value of the zinc to zinc 2 plus, and I say, I just want to know how much the electric value is going to be for that, right, or the voltage value for that, and then I separately want to look at the copper 2 plus side, and what is the E for that? Those are called half cells. We need to be able to find half cell potentials or half cell reactions. And as it stands right now, you have to complete the circuit in order to get the full reading for the cell. All right, so that becomes problematic when you want to actually take a reading of a half cell, because the way that this works is that the standardized E cell is going to be equal to the standard cathode value minus the standard anode value. Okay, so in the example above, copper was the cathode and zinc was the anode. So the E cell for this reaction is going to be equal to the half cell of the copper, which is copper 2 plus copper, okay, minus the E cell of the zinc 2 plus zinc relationship. Now, you can find these on standardized tables, but we need to understand that to a greater degree. So what the next lecture is going to focus on is how we can understand and utilize half cell potentials. And specifically, in order to obtain these values, we have to set a standard half cell to 0 and base everything off of that reading. And it turns out hydrogen is the one we use for that. So in the upcoming lecture, we're going to discuss the hydrogen half cell, how we set it to 0, and how that gives us the basis for calculating all the other half potentials that we can pick up on charts for this standard state. So that will be the next lecture. That wraps this portion up. So if you found it helpful, remember to like, because that boosts us in the algorithm. We can get out to more people, and I will be able to keep providing you with quality content as you're going through your courses, learning, preparing for whatever career you're going with. Remember to subscribe. If you hit the little bell, you'll get updates every time we're putting videos out. And we want you to subscribe because that allows you to interact with the community a little bit better. Obviously, that helps the algorithm too. And then finally, if you have any questions, please feel free to comment, and I will try to get back as soon as possible. We're going to be working through this electrochemistry course in the next week or two here. Final note, head on over to chemcomplete.com. We have lots of free resources over there, and we also have private one-on-one tutoring with me that is available. So if you're struggling with electrochemistry or any other topic, I have very affordable tutoring. One-on-one, you'll have a private Zoom call with me, and I will coach you through whatever you need. And we also offer guides that I have personally written. I am working on a full textbook right now, but that obviously is going to take a lot of time before I can push that out. But as always, thank you for your support. You're supporting the channel just by watching, and I will see everybody next time.